The Industrial Revolution transformed the world beyond recognition. And today, we still rely on many of those groundbreaking advances, whether we realize it or not. Beneath the River Thames is a tunnel built using an innovative technique that's still relied upon. It's amazing to think that this is the very spot where the project started. It's really incredible because it's radically changed the world beneath our feet ever since then. In the Netherlands is a building designed to tackle rising floodwaters and create space for the future.
What they were trying to achieve here was hugely ambitious. And once they got on that journey, they weren't going back. It still impacts life today.
And the home of the world's first electronic computer. It was built to defeat Hitler, but it relied on an idea championed by Napoleon.
I kind of love the fact that you're not going to trace computers back to, say, the 1980s. You're going to all the way back to a machine made to deal with textile fabrics. I mean, that's just amazing when you think about it.
Born from the flames of the Industrial Revolution, and once celebrated as pioneering achievements, these are the forgotten stories of the sites that built the modern world. In London, buried underground, lies a dark route that's been in use for over 175 years. Begun as a project to transform the capital, it would spark a subterranean revolution. Walking through these quite typical London streets, it's easy to miss the fact that this is the site of one of the most innovative and impactful projects of the 19th century. The creation of this tunnel was thought impossible by many.
The structure's the first of its kind. It's never been done before.
It's important in its own right, but even more so is how it still informs modern engineering projects. The technique adopted remains the way we do tunnels today.
But they had no idea of the impact it would have on the rest of the world. It was extremely clever and innovative, but also very ambitious for its time. Beneath the streets of East London is one of the oldest sections of the city's many underground rail lines. But this stretch has a greater claim to fame.
It's used by commuters every single day, and it runs from Wapping on the North Bank to Rotherhithe on the South Bank. But actually, it is a unique part of history.
People riding the train, commuting daily, wouldn't realize that underneath is something truly remarkable.
As the trains pass through, the tunnel seems pretty standard. But what's special about it is the location and how it was built.
What was done here had been attempted by others before, but this was the first successful attempt.
This is the Thames Tunnel, the first tunnel to be dug underneath a river.
So at the beginning of the 19th century, London was probably the busiest port in the world, and there was a lot of commercial activity. But to actually physically take items from, say, Wapping to Rotherhithe, you had to go through some of the most congested streets in London.
Tunnelling below a navigable river had never been achieved before. Here, it would take almost 2 decades and claim at least 6 lives in the process.
This project was mammoth in scale and far greater than anything anyone could have anticipated.
The final structure lies beneath the 300-metre-wide River Thames. And incredibly, at their closest, the riverbed and the tunnel roof are just 4 metres apart. Today, Wapping Station resides in the old Northern Access Chamber. But on the other side lies a similar structure, and this one marks a key moment in history. With the tunnel still in use, it's hard to get close to it, but there is an area that still exists almost as it was. This is the site where Marc Brunel began his pioneering Thames tunnel. Brunel and his team got underway here in 1825, and both the location and design of this structure were vital to ensuring a successful start. Is that the sound of trains underneath us?
It absolutely is, yeah. The London Overground, going between Wapping and Rotherhithe Station.
So what is this space?
So we're standing 16 metres underground in a tunnelling shaft. It was built by constructing a 25-ton iron hoop and then covering that with bricks to make this cylindrical structure that you can see around us.
This area here is the bricks that they were putting on top of the ring.
Exactly. And what was really clever about Marc Brunel's idea is that he used the weight of the shaft itself to sink directly into the riverbed. So think of it like an enormous pastry cutter going into the riverbed.
When deep enough, this shaft would provide access for the workers and equipment. Once they'd reached a depth of around 25 metres, then the tunnelling under the river would begin. It looks like such a simple structure, but this really was a genius mind at work, because the engineer understood the disadvantages of the surrounding soil, but embraced it to create something truly epic. The greatest challenges and dangers, however, still lay ahead.
The idea of tunnelling under the Thames wasn't new. In 1807, Cornish miners attempted to actually construct a tunnel, and they did get reasonably far before the sewage-ridden waters of the Thames flooded the tunnel and the whole project died a death. So the idea was abandoned. Indeed, most people didn't think it would be possible.
But Brunel believed otherwise. He'd come up with a plan to overcome the risk of a cave-in, and his inspiration came from an unlikely source.
Based on an entry in Marc Brunel's own diary, he observed a piece of ship lumber, and on it he saw a worm digesting the wood and excreting it. And in this excretion, it was forming a lining. And this was the idea that sparked the thinking for his own tunnel shield.
The tunnelling shield was a relatively simple idea, but it revolutionised what was possible. An iron frame, 12 cells across and 3 cells tall.
The key thing underpinning Marc Brunel's tunnelling shield is that the roof and the sides of the tunnel wouldn't collapse. You have an iron frame and in front wooden slats with a number of compartments where workers would dig into the tunnel.
Outside the tunnel shaft is a model of 2 such compartments. So how exactly does this contraption work?
One of the miners would be inside each of these cells. They'd basically be at the tunnel face.
It's tiny. Standing here gives you a real sense of just how small and cramped the space was for the workers. So they were chipping away at this end. Like, how fast were they going?
Not very fast at all. You know, they're doing all of this with hand tools. It's really painstaking, back-breaking work. So they're only really moving, you know, a couple of inches at a time.
You'd remove one of the wooden slats, dig about 9 inches, about the size of an average brick, then you put the wooden slat back. And when all of this had been completed, you'd move the tunnel shield in 2 parts. And then behind, you'd have men at the back who were brickies laying the roof above to make sure it didn't collapse.
It was this invention that made digging the Thames tunnel possible. And it's why this site remains one of the most important engineering achievements in the world. It must have been really ingenious for its time.
Absolutely. Marc Brunel was the first person to come up with the idea of the tunnelling shield, but his ideas are still being used today to build tunnels. If he went to any of the tunnelling projects that were happening today, he would recognise his technology.
With almost 200 years having passed since Brunel began this tunnel, his innovation has spread across the world and received a number of upgrades. But modern tunnelling projects still rely on the core idea, as can be seen at a site on the other side of the world in Australia.
The Snowy 2.0 project is an epic hydroelectric project that is being built to provide energy for more than 500,000 homes all at the same time. It will link 2 existing dams with a very large tunnel. That tunnel will be 27 kilometres in length, and there will be an underground power station in the middle.
The new tunnel will help upgrade the original Snowy scheme that began in 1949. Activity at the site is growing. A major step in the construction is about to begin.
This face is where we'll create the main access tunnel, our primary access for all of our people, vehicle and equipment.
To dig the tunnel, a TBM or tunnel boring machine will be used. At its face, there are 66 cutters that will break down and dig through the rock. But at this stage, a familiar problem arises.
The challenge that Brunel faced is still the challenge we have today when building tunnels. When you remove that material, there's always the risk of collapse.
Marc had a tunnelling shield which was designed to keep his workers safe from the exposed rock face, and we have a shield that also protects the workers. The difference is that Marc advanced 4 inches a day and we will advance up to 20 metres a day.
Inside the shielded front section is the equipment to build the tunnel lining. This technology and approach to tunnelling has been adopted the world over. But modern TBMs also had several other upgrades. And one in particular could have made all the difference back in Brunel's day.
There's several dangers inside the tunnel: flooding, fires, toxic gases. So in case of hazard in the tunnel boring machine, we go inside the refuge chamber. The refuge chamber is designed to support life for 24 persons for 24 hours, so that the whole team can wait for rescue to join.
A number of problems Brunel faced in tunnelling under the Thames, like the sewage, disease, pleurisy, and so forth. But really, the most important problem was flooding.
Steam engines housed in this building pumped out any water seeping through. But London's soft clay, combined with the tunnel's proximity to the river, meant that despite the tunnelling shield, a catastrophic flood was still a real possibility. When you think about the workers having to dig under this huge body of water with just an iron frame and steam engines pumping the water out, it must have been so terrifying. And soon enough, the inevitable occurred.
In 1828, the most serious flood to date happened, which nearly killed Marc Brunel's son, Isambard Brunel.
Now, the other workers decided to escape through the tunnel shaft, but Isambard wanted to use the emergency exit, and when he got to the door, it was locked. And after making a huge amount of noise, someone eventually heard him and unlocked the door. But the 6 people he was working alongside sadly drowned. Following the disaster, the investors pulled out, and the project shut down for 7 years. They weren't even halfway across. When Brunel finally managed to fund the building of a new and improved tunnelling shield, ahead of them still lay 6 more years of digging.
To think that this project was achieved in the 19th century with not even half of the tech that we have today is incredible.
On the 25th of March, 1843, the Thames Tunnel opened to the public.
Brunel had thought it was going to take about 3 years. It had taken 18.
Millions of people flocked to see the tunnel. But due to spiralling costs, commercial access routes were never built. In this regard, it had failed. In 1869, however, it found its true calling. After some modifications, the first steam train rolled through.
The Thames Tunnel, despite all the challenges facing the engineers, still proves important to the transport network today.
By achieving what many had thought impossible, Brunel had set in motion a slow subterranean revolution. The challenge of digging a tunnel involves dangers and difficulties that we can't really avoid. Brunel's idea has been developed in terms of extra protective measures at the cutting face and more safety features, but essentially Brunel's idea, his achievement, has stayed the same, and it's radically transformed the world beneath our feet ever since. In Australia, the latest in a long line of tunnelling projects is only made possible because of this state-of-the-art machinery that has built upon Brunel's ideas.
The modern-day tunnel boring machine is an incredible piece of machinery. It is essentially a mobile factory that is efficient at excavating the tunnel, but more importantly, keeping all of the people safe while doing so. So Marc's achievements, they were visionary, they were ahead of their time, and we pay homage to what he did.
In the low-lying Netherlands stands a building that permanently altered the shape of the country, while a nearby site reveals it will likely happen again.
When you zoom in on this flat, featureless landscape, right at the heart, what catches your eye is totally man-made, and it's unique.
It has the feel of some fortress or castle or some defensive base. But the clue of what it really was rises above it: chimney. Hidden inside is a secret of why this country looks the way it does today.
It's just beautiful, isn't it? Got all this highly polished brasswork. The smell of oil is just hanging in the air.
It looks really complicated, but this structure was designed for one purpose, and it just needed a lot of power to do it.
60 miles away lies a contrasting site that offers clues to a more recent chapter of this tale.
This man-made features huge, huge, very solid, very substantial, concrete structures that are totally out of place.
This site is really different. It's from a different age entirely, but they are both part of the same story.
Both sites were born from desperate situations, and each was built to battle the waters that surround them.
This country has had a strong relationship with water for centuries. Sometimes this has worked in its favor, and other times it's been a disaster.
Standing on the water's edge in the southwest of the country. Today, these structures are part of a museum site commemorating a devastating event.
On the night of the 31st of January, 1953, in the middle of winter, there was a massive storm out at the North Sea, and it hit a huge area across Europe.
Across the country, the storm defenses were overwhelmed. The dikes burst, and the sea just tore through the region.
These concrete forms aren't only a memorial. They were part of the emergency response.
We zijn hier in Ouwerkerk, op Schouwen en Duiveland. Op de plaats waar in 1953 een van de grotere dijkgaten waren na de watersnoodramp. Die dijkgaten die hebben ze gesloten op deze plaats met deze hele grote betonnen bakken, caissons, afkomstig gemaakt in Engeland.
The caissons had originally been built for use after D-Day in the famous Mulberry Harbours.
Van de Tweede Wereldoorlog nog een aantal van deze hele grote caissons. Van 60 meter lang, 20 meter hoog. en 20 meter breed beschikbaar waren.
Towed from England and sunk here, they helped to stem the flow. But a huge amount of damage had already been done.
100,000 people were evacuated. 340,000 acres of land was flooded. 1,836 lives were lost. It was devastating.
Unfortunately, destruction like this had long been feared.
That flood was a major disaster, but it wasn't the first time that the region had been overwhelmed or at the mercy of rising waters. The country had been dealing with the challenge of flooding for centuries.
With around a quarter of the Netherlands below sea level and another 29% at risk of flooding, coastal defences are vital. But the danger also comes from within, when storms push the waterways and lakes to breaking point. In the 19th century, it was this inland battle that had the capital city searching for a solution. This structure, the Crucius pumping station, was built as one of the 3 sites designed to safeguard the future of Amsterdam.
They're high quality, they are beautifully made, they're unique. But the thing that obviously catches your eye in the centre are these massive arms, like a huge spider in the landscape.
Once you come in, it draws you in, and then you see that the whole place was built around a machine.
This site marks the moment when the Netherlands fully embraced the technology of the Industrial Revolution. But they were embarking upon a colossal challenge. Elise van Mellis is the current director of the site.
Rond 1800 was het hier één grote watermassa. De grootste binnenzee van Nederland.
Known as the Haarlemmermeer, it was formed when a series of smaller lakes grew in size and merged together.
In 1836 waren er 2 stormen in november en in december. Die zorgden ervoor dat eigenlijk dus de dam tussen Amsterdam en Haarlemmermeer in doorgebroken werd. Dus het was een enorm gevaar voor Amsterdam, dus er moest een oplossing komen.
Following years of debate, a controversial decision was made to build just 3 steam-powered pumping stations to drain the entire lake. This was a radical plan. Steam power had never been used on such a scale.
I would not have liked to have signed off on purchasing this machine. It's incredibly expensive, it's very complex, and at the time the technology, although it was tested, it didn't necessarily come with any guarantee.
The plan's critics instead wanted to employ windmills, a technology that had been in use for hundreds of years.
Deze molen maakt dus onderdeel uit van de molenviergang. Het zijn dus 4 molens die het water naar elkaar toe malen. En dat gebeurt nog steeds op de authentieke wijze, zoals de molens gebouwd zijn, ruim 200 jaar geleden.
Originally, this area was a vast peat bog, and years of extraction would see it drop to a staggering 5 meters below sea level. The 4 windmills have been hard at work ever since to keep the area drained.
Omdat we dus zo diep onder zee zitten, moet al het regenwater hier dus weggemalen worden. Anders krijgen we weer een plas.
So in the 1830s, with Amsterdam facing the threat of deadly floods, windmills seemed to be the obvious solution. But they simply weren't enough, and it took the king himself to say so.
De beperking van windmolens, dat zegt het woord al, windmolen. Je moet dus wel wind hebben. In Nederland is er niet altijd wind. En daardoor is de capaciteit of de werking van een windmolen beperkt.
It wasn't just about being able to guarantee that power, though. It was also about how much power would be required for a job of this size. The 4 windmills here drain an area of 1,200 acres.
But in this new area, they wanted to pump out 40 to 45,000 acres. So the scale of the ambition they were trying to reach was huge.
So if we look at this old, fantastic steampunk technology, how did this save the modern city of Amsterdam?
This is the world's largest Cornish beam engine used for pumping the Haarlemmermeer dry. It's called the Colossus engine.
The thing that always strikes me about stationary engines is how quiet they are. So you can hear things moving and you can hear valves, but it's almost meditative.
6 boilers hidden in the back building produce the steam required to raise the 85 tons of weight.
Steam from the boiler room enters the engine room via this huge diameter riveted pipe, and then via the inlet valve admits the steam to the bottom of the cylinder, thereby raising the piston inside upwards.
As the central piston rises, it forces up the ends of the beams that surround it. Then, as the piston drops again, those beams are pulled back down.
On the outside, the other end of the beam is connected to pumping rods, and then they bring up huge amounts of water.
Each pump raises 8,000 litres of water up 5 metres with each stroke.
The engine was fired up in 1849, and the task of draining the lake began.
It could drain 70,000 gallons of water every 60 seconds. That's about an Olympic-sized pool every 8 minutes. The scale of the innovation and the advancement was enormous.
Teamed with 2 other similar pumping sites, the job took just 3 years to complete. Soon, hundreds of steam-powered pumping stations of all sizes were installed across the country.
Suddenly, you bring the invention of the steam engine along and all that pent-up energy in a lump of coal, and between 3 sites, they can do the work of 240 windmills.
While the defence of Amsterdam had created a sense of urgency, this was not the only driving force behind the project.
De impact van het droogmaken van dit gebied voor en Haarlemmermeer en Amsterdam was enorm groot. Amsterdam kon natuurlijk veilig droog blijven, maar er ontstond hier een enorm groot gebied dat landbouwgrond opleverde.
We talk a lot about these engineering projects as nation-building enterprises. And quite literally, in this example, it is literally building the land.
Over the years, this new land has become of vital importance to the Netherlands.
When you fly into Amsterdam and you land in Schiphol Airport, you're actually touching down on an area that used to be completely underwater. So you can see that this still has a huge effect on the modern country.
But even today, all of this relies upon the continuation of what began here over 170 years ago.
It's not just about draining land and then job done. You have to continue to pump the area to ensure that water doesn't flow right back in.
This site ran until 1932, when it was retired and preserved as a monument to this breakthrough technology.
The days of the steam engine may well be over, but on other sites all across this area, there are still new pumps being put in, old pumps being refurbished. The moving of water still continues every single day.
The 2 sister sites, although updated, continue to be used to this day. In Zeeland, the 1953 flood has left a lasting impression.
De watersnoodramp heeft heel veel betekend voor dit gebied. Alles was vernield. Wat er groeide en bloeide en veel gebouwen kapot. Er zijn heel veel nieuwe gebouwen gekomen, nieuwe wegen gekomen. Maar de dijken waren kapot. Daardoor hebben we nieuwe, grotere dijken gemaakt.
A year after the disaster, a major engineering project known as the Delta Works began to rebuild and reinforce the coastal defences.
You have to view these solutions in a system. You can't simply just look at the pumping stations as separate from the flood defenses that actually keep the sea out.
Dus halen we dijken en duinen weg, is Nederland gelijk de helft kleiner. Is het onder water, is het zee.
You can see that this is a system that's all working together to keep the lands dry and safe. And it is a story that is ongoing.
In the UK lies a forgotten piece of the story of our digital world. But it owes a surprising debt to an older French invention.
When we come to this building, it's fairly bland, quite utilitarian really. And you wonder, what's this function? Is it trying to hide something?
From the outside, nothing much seems to be going on, but what happened inside shaped the course of history.
This was where some of Britain's greatest minds came together to defeat one of the biggest threats of the 20th century.
The machines built here helped win a war. But one of these remained overlooked and classified for decades. And incredibly, it utilized an idea pioneered over 100 years earlier.
This one design innovation, it changed the lives of 19th century textile workers. I mean, well, frankly, it changed all of our lives.
What links these two machines is not the purpose for which they're built, rather how they were programmed.
What's so interesting is that the design of it allows it to have this huge impact across the world in ways that, I mean, I'm sure they didn't even imagine.
Just south of Milton Keynes, in what was formerly Block H of Bletchley Park, now stands the National Museum of Computing. Inside is a rebuild of the Second World War machine created to decrypt German communications.
So this is the Turing Welshman bomb, a replica of one that 211 that were made. And its purpose is to find the basic settings for all the Enigma machines that were used on a particular radio network.
The Nazis were using Enigma to coordinate attacks on British supply ships in the Atlantic. But through the capture of an Enigma machine in 1941, the bomb was built. It massively reduced the number of possible encryption settings needing to be tested.
When it stops, as it's done here, it provides you with some information that you need to be checked.
The bomb doesn't give you the full answer, you know, the exact details, but it gives you a pretty good idea. It gets you close.
Cracking Enigma gave the Allies a chance to keep a step ahead. But as early as 1941, they started picking up a new signal. These were messages encrypted by a Lorenz machine.
The Lorenz was far more complicated than the Enigma. I mean, the number of theoretical options was more than the number of atoms in the universe. I mean, that's what we're talking about.
This was used by the German High Command, typically, for communication with generals in the field. This is high-grade intelligence. This is really the gold dust. This is what you need to know in order to change the course of a battle or even the course of the war.
But for the Allies, there was a major problem.
Unlike the Enigma, the Brits didn't actually have a copy of the Lorenz to take a look at. So they had to do their best guess and build themselves a machine that would help them out.
In August 1941, a mistake by a German operator sets things in motion. It takes months to first understand how Lorenz works, then years of building machines to speed up deciphering the messages. But by early 1944, they had created the world's first electronic computer, Colossus.
We're standing next to our Colossus rebuild. in the 1940s. They made 10 of these things. Number 9 stood exactly where our rebuild is.
What Colossus did was be able to decipher a message within hours. In the past, it could take weeks.
The Allies hoped this was the advantage they had been waiting for, and they'd soon use Colossus for their greatest gamble of the war, D-Day.
Colossus really lives up to its name, not just in terms of its huge size, but on the impact it had on World War II.
But one key part of this machine relied on an idea with a surprising origin. It had first made an impact in the French textile industry over 100 years earlier, and it would play a vital role in the birth of computing. In 1805, Emperor Napoleon Bonaparte hoped to boost his country's competitiveness in the textiles market by supporting the manufacture of this machine, the Jacquard loom.
Before the Jacquard loom, the creation of these patterns was extremely slow and laborious.
It literally, on some occasions, could take months to actually finish a patterned silk garment. So that was the idea, to speed up the process.
Jacquard looms changed the textile industry, which sounds exciting, but people were angry. I mean, they had violent protests. They broke apart machines, they threw things at them. It made it a pretty dangerous place to work.
What incensed the weavers was that with this machine, their services were no longer needed. Prior to this, weaving had remained relatively unchanged for centuries.
Tisser, c'est vraiment assez simple. En fait, il suffit de croiser des fils. Donc, sur un métier de ce type, on va retrouver à l'arrière du métier ce qu'on appelle les fils de chaîne. À l'avant, ici disposé sur une petite fusette en bois, on va avoir le fil de trame. Et l'objectif, en fait, c'est simplement de croiser ces fils, et c'est ce qui va nous permettre de créer le tissu.
For patterned cloths and silks, however, it required larger looms, more workers, and the skill to create intricate designs.
It's this interlacing of the threads that forms the cloth, but it's the order of the weft weaving and passing over the warp that forms the pattern.
With Joseph Marie Jacquard's new invention, the industry changed overnight. His loom was automated. It took its direction not from a skilled master weaver, but from punch cards.
C'est très simple, comporte deux informations. Soit vous allez y retrouver un plein, soit vous allez y retrouver un vide.
Where there's a hole, the pin would come down and lift the warp. Where there is no hole, the pin wouldn't go down and the warp would stay stationary.
Donc, lorsque je vais appuyer sur la pédale, ne vont se lever que les fils dont je vais avoir besoin pour la réalisation du motif. Ici, si on s'approche, par exemple, on peut constater qu'il y a beaucoup plus de fils beiges qui se sont levés pour pouvoir former le motif de mon ovale. Ensuite, il me suffit de passer la navette pour croiser mes fils et commencer à tisser.
Other inventors quickly saw the potential of this idea and took it in new directions. By the mid-1830s, English mathematician Charles Babbage was working on designs for something he called an analytical engine.
Babbage's idea is again quite simple, and that is to punch cards instructing the analytical engine to work out a particular equation.
While he never saw it completed, it is widely considered to be the world's first computer. His close associate recognized the importance of Jacquard's influence.
I think Ada Lovelace sums it up beautifully. The analytical engine weaves algebraic patterns just as a Jacquard loom weaves flowers and leaves.
This same idea for inputting data would be used for Colossus, but in an updated version with the intercepted Lorenz message being transcribed onto paper tape.
On here, our ciphertext is presented on the paper tape. My data is my ciphertext. That's the kind of similar idea to a punch card.
By looping the data input, they could quickly rattle through the many possible Lorenz machine settings.
To read a punch card, you need to drop needles through holes and register electrical contacts. On the Colossus reader, it's optical. You're shining a light through the holes and detecting the light when it comes through. This machine has 5 parallel paths through it, so it's actually able to do 25,000 logical operations per second.
Now able to decrypt a message within hours rather than weeks, the Allied forces chose to press home their new advantage.
So the Colossus machine became operational in 1944, and it was so good at tackling all these Lorenz encryptions that they ordered even more of them for June 1944.
D-Day was the chance to strike a major blow against the Nazis. But for their plan to succeed, they'd need the help of both Colossus and the bomb.
In preparation for D-Day, the Allies kick-started what they called Operation Fortitude, which is about deception ahead of the landings at Normandy.
Wrong information was deliberately diffused by the Allies to suggest that D-Day would take place in Calais rather than Normandy.
The machines here in Bletchley monitored and decrypted the enemy's communications, and soon they had the answer they were waiting for.
Hitler wanted no additional troops sent to Normandy. He was convinced that no Allies would land there.
That yes or no decision would have been done on the collective input from Colossus decrypts and also Enigma decrypts.
While not every message could be decrypted by Colossus, the sheer volume of work it tackled shows its importance to the war effort.
So in total, Colossus deciphered about 63 million characters, which is the equivalent of reading all of the Harry Potter books over and over again 11 times.
It built upon ideas and theories that came before it, but Colossus was a pioneering achievement in its own right. After the war, Colossus remained top secret for years, and as a result, its impact has been overlooked.
I don't think the average person does know about Colossus, and that's a shame. But the people that worked on these machines, some of them in particular, went on to become very important people in the evolution of the computer industry, particularly in the UK. These people were steering our future, albeit subtly maybe.
So we don't need punch cards anymore. We don't have these huge data machines, but the Colossus is part of what got us to where we are today. And if you think about how far we came, it's kind of incredible to imagine, how far we might go.